By the end of this lesson, we'll be able to describe the transfer of energy into, out of, or within a system in terms of power. We need to know what power is, the rate at which energy changes with respect to time, either by transfer into or out of a system, or by conversion from one type to another within that system. The symbol we use for power is capital P. We use the watt as our unit of measurement. For watt, we use capital W. Be careful not to confuse capital W, the unit, which is the watt, with capital W, the symbol, which is for work. And then we should also throw in there lowercase w for weight. Another version of the watt would be a joule per second. Remember that a joule is a kilogram times meter per second squared. Divide that by a second, and we get kilograms times meters per second. So simply put, power is the amount of energy being transferred or converted divided by the time that it took for that transfer or conversion to occur. It's the rate that energy is being transformed. In mathematical terms, we get an equation that looks like this. Our average power equals our change in energy over our change in time. Remember that our change in energy, through the work energy theorem, is equal to the work done on or by the system, divided by time. We've got a fun derivation that we can use here, where we see a lot of substitutions and call back things that we hopefully remember. The average power, here we go. We know that work equals force times displacement, so we can do F times D over delta T. What is displacement over time? Velocity. So another way we can write power is force times velocity. Remember that our velocity vector has to be acting in the same direction as the force acting on it in order for work to be done. So we can show from our average power what our instantaneous power would be using the component of the constant force that's parallel to the object's velocity, which just becomes FV cosine theta. You can find power from graphs. Here's an example on the bottom left of a force versus velocity graph. The data on there doesn't matter, but the slope of the graph would be force versus velocity, force over velocity. So that's not what we're looking for. Meanwhile, the integral, the area under the curve, force times velocity, would give us power. Remember that force is directly proportional to acceleration. So maybe it's an acceleration versus velocity graph, which sounds really weird. But if our acceleration is changing as our velocity changes, we can go through and multiply mass times that acceleration to get a force. Don't forget about those kinds of relationships. Here's an example. A student pushes a box across a horizontal surface with a constant velocity. The box has a mass of 15 kilograms and the coefficient of kinetic friction between the box and the surface is 0.2. If the box is pushed for a distance of 10 meters and it takes 5 seconds to travel this distance, calculate the power exerted by the student while pushing the box. A strategy that's often helpful is to underline or highlight important information. So you can do that if you see a variable, like this is mass, so this we could put m. Coefficient of kinetic friction is 0.2, so maybe we want to put a little mu note there. Whatever works for you. Just do something to keep your focus and your thoughts in a nice and ordered manner. We learned about the givens and then the unknown, the whole guess strategy. You can do that no matter what the physics problem is. List out the information that's given to you. If that keeps you organized, please do it. And of course, we want to calculate the power. So we're moving on a horizontal surface. So we have this push force going on, and then we have this frictional force. Then, of course, we have our weight force down and the normal force. Because we know that power equals work over time, and work equals force times displacement over time, the force that we're looking for is going to be the force of the student, so that push force. Well, our constant velocity up here tells us that the push force has to equal the frictional force. stuff that makes it go minus stuff holding it back equals 0, so our frictional force equals our push force, and our frictional force equals mu times Fn. Because we're on a horizontal surface, that just means Fn is going to be equal to mg, so it equals mu mg. So mu is going to be 0.2, mass is going to be 15, g is going to be 10, times our displacement divided by the time that it takes, which is 5 seconds. Hopefully when you calculate all of that, you get your power equals 60 watts. So what's next? Complete your practice. For more practice, there's your AI prompt. Ask each other, ask me, and keep asking until you get it.